The second third of this section is the washer method. Use the washer method to cover solids of revolution that have holes in them. So here's a nice picture of a washer right here. Okay, on this washer, if I draw an axis of revolution through the washer, and I draw a representative rectangle on that washer, then hopefully you can see that as I revolve that representative rectangle around, I wind up creating that washer. Rather than that rectangle coming all the way down and me revolving that around and creating just a disk, because my rectangle is off the axis of revolution, as I rotate it around, I wind up with a hole that's created. And that's why it's called a washer. Okay? So then if I slide this over the course of some entire shape, then as I revolve that around, I wind up with a whole bunch of washers that wind up creating an entire volume. Okay, so to develop the washer method, we need an axis of revolution, in this case through the center of this washer that you can see. The representative rectangle would have a length capital R of x minus little r of x. So the reason for that is this guy, just like in the disk method, was my capital R of x, the total height of that representative rectangle back to the axis of revolution. But because I don't want this involved in that height, I have to subtract it off, and that's going to be my little r of x. So what happens is I have a big radius. This radius goes all the way out to the edge of the figure that we're creating. And I'm subtracting the little radius, whatever that is. Okay? That's why we're using big R and little r. The bigger radius and the little radius. So the representative rectangle would have a length of big R of x minus little r of x, where big R is the outer radius, little r is the inner radius. The width of the representative rectangle in this case is going to be delta x. Now the area of the representative disk, the disk, is pi r squared. The area of the hole is pi r squared, but notice that I'm using big R and little r. So I'm using big R squared and little r squared for the outer representative disk, and then this would be a disk. But I'm actually making it a hole. So just like back in the 4th grade when we had a rectangle and we subtract out a hole to find that area, that's what we're doing here. Now the volume is pi times the radius squared times the height. So we have that pi sitting here. Our slider is moving from A to B, so that's going to give me my height. And then we have the outer radius minus the inner radius, which is basically giving me the area that I'm actually creating. Okay? So as I revolve that around, I wind up with my shape. This method is what you would use to create the shell of a jet engine or something of that nature. Okay? So, jump right in and let's see if we can figure out this problem. Remember, before you really set anything up, you want to try to visualize what it is that you're creating here. So find the volume of the solid form by revolving the region bounded by these two functions about the x-axis. So first of all, it says about the x-axis. That's this axis, so I'm revolving that shape about the x-axis that way. So I'm creating this region right here. This is the thing that they're talking about. If I revolve that around, what does it make? So what's going to happen is this thing is going to get revolved. This shape right here gets revolved around the x-axis. Okay? So this whole thing right here is my cross-section. So I need to picture that also sitting over here, right? But also that thing comes out of the screen and goes into the screen and makes this shape around. Yeah, the bottom of it, this outside portion is going to look like a bowl. Okay? So like if I grab this thing and held it in my hand, using the bottom, if I called that the bottom, okay, if I hold it upright, if I use this bottom right here, then it would look like a bowl, a parabolic bowl. But inside, that's going to look more like a funnel, right? I think somebody said a funnel. So something you could picture, if you've ever been to the mall and you've seen those, they're usually yellow, where you dump a coin in and then it spins around for forever and then finally it dumps into the bottom that has, you know, thousands of dollars in coins in it, because that's what everybody does when they go there and they just watch it mesmerized. That's basically what's created here on the inside, okay? On the outside we have that bowl type shape though. So try to picture that. That usually helps when you're trying to set up your representative rectangle. So draw in the representative rectangle on here. These representative rectangles also need to be perpendicular to the axis of revolution. Otherwise, you're not going to create a washer. You're just going to create like a brick. Okay, what else do we need to do maybe? We have to find what? We got to find our intersection points so we can find our bounds. They look like 0 and 1, but we have to be sure. So we got to do what? Okay, set them equal to each other. We have the square root of x equals x squared. No. We got to actually solve it. Well, I don't really know how to work with this square root thing. So I'm going to square both sides. That gives me x here equals x to the fourth. Now the bummer there is I just introduced two more solutions to this that weren't there in the first place. But we can continue. Now what? Subtract x from both sides. I have x to the fourth minus x equals 0. X times x to the third minus 1 equals 0. X equals 0. X to the third equals 1. So x equals 1. Not plus or minus 1 as a third root. So we do have 0 and 1, which is nice.
Now let's do this.
Okay. So what I'm going to recommend that you do is actually define your big R and your little r, like on this graph. So where my slider is right now, big R equals what? Yeah, the value of the function is the square root of x. That's the upper function. And then, so that's this guy. Little r, I don't really have a whole lot of room here. Little r of x equals x squared. So now what? Now set up your integral. Yeah, so v equals pi. Really we're doing pi radius squared height again. Integral from 0 to 1, because those are my bounds. My slider can move from 0 to 1. Big R, which is the square root of x. Okay, now is the square root of x being squared? Yeah? Minus dx. So now what do we do? Simplify. V equals pi times the integral 0 to 1 of x minus x to the fourth dx. And then we integrate. V equals pi times we need to integrate and we're going from 0 to 1. Now the 0 is going to make everything disappear, so really I'm just plugging in the 1. V equals pi times, okay, minus 0. V equals 3 pi over 10. And you're done. Next example, find the volume of the solid formed by revolving the region bounded by the graphs of those about the y-axis this time. So this time, we're doing this. Now let's try to picture what that shape's going to look like. I have everything drawn in here already. Y equals x squared plus 1 is this. Y equals 0 is the x-axis. X equals 0 is the y-axis. And x equals 1 is this line right here. So make sure you understand how to put those lines on there. Y equals something is horizontal. X equals something is vertical. That creates this region right here. So or maybe like an Easter egg holder. Yeah, that could be. Except that was just flat. This thing is going to be totally round.
A crater. It got hit by a crater.
I like
It got
that.
hit by a crater?
It's an egg holder.
I'm making something else.
All right. As long as you can picture what it looks like in your mind, then you can kind of picture how this thing's supposed to go. Now, I have note. Be careful in this case, 2 separate integrals are needed and the problem requires us to revolve around the y-axis. Why? That's right. Actually, doing this problem a different way would be nice. Like, it'd be nice if I could do this about the x-axis. Or, I'm sorry, if I could do this using vertical representative rectangles, right? Because then my slider would go all the way to here, no problem. But I can't because this is not revolving about the x-axis, and my representative rectangle needs to be perpendicular to the axis of revolution. We can't change it. We have to revolve around this. The problem asks us to, okay? So we're required to make a horizontal representative rectangle. But now as this thing slides, it gets caught right here, which means we're going to have to make a second horizontal representative rectangle, and we're going to have to set up 2 separate integrals. Okay? It can't be avoided here. We have to do it this way. Actually, it can be avoided in the next section, but we don't know that yet. So what I'm going to do is I'm going to draw a little dotted line over to remind me that this slider here goes just in this region, and this slider goes just in this region. All right, so we need to figure out where that occurs. Where does it occur?
1.
Yeah, that's kind of an easy one. We aren't really assuming it's 1. We know it's 1 because this is formed by this parabola crossing the y-axis, and that means that the y-intercept is going to be where that switch happens, and that's at 1, okay? So I can set up my integrals, actually, and my first integral for this guy is going to be from 0 to 1, and my second integral is going to be from 1 to
Maybe 2.
maybe 2. It looks like 2. How can we figure out if it is 2? When x is 1, we have our intersection point. So I can plug 1 into this. 1 squared is 1, plus 1 is 2. So that does give me my 1 comma 2 here. This gives me my 0 comma 1 there. And now, since I have 0, 0, I have everything I need. Now, what method am I going to need to use? Let's do this one first. What method will I have to use here? That is the disk method. As this revolves, this shape right here is directly on the axis of revolution, which means that there's no hole being formed. So I can use the disk method on that. So let's set it up.
V equals 5 times the integral
0 to 1.
of
So what is it?
y equals 0 because it's the y-axis.
What's the radius? It's 1. We go from here out to here. That distance is 1, and it's a constant 1 the whole time. So it's just 1 squared
Y
dy. Now what?
is pi y.
We got to set up the other one, but what am I going to have?
Pi y.
What do we need? Plus, good. We're adding these two integrals together. Pi integral from 1 to 2. So, this is where it gets tricky. So, yeah, let me explain that. This outer radius goes from the y-axis out to the outer limit of that representative rectangle. So that distance right there is my big R of y. That is a constant. It's 1. So I need 1 squared minus our inner function is little r of y. We have to solve it for x because it needs to be in terms of y because of the fact that we're revolving about the y-axis. So we got to take this equation and solve for x. Y minus 1 equals x squared. When you take the square root of something, you have to include plus or minus, right? When you take the square root of both sides of the equation. Which side are we looking at here? Yeah, we're looking at the positive side, so we don't need the plus or minus here. All right, now what?
Now we can take that answer and
So square root y minus 1, and that is squared. All of that is with dy. So simplify. V equals okay, so we're going to rewrite 0, 1, 1 squared dy plus pi integral 1 to 2. What?
1 minus y minus 1.
Okay, so that's
Y minus 2.
no.
Negative y.
No. Plus 2. This is 1 minus y minus 1. So 1 minus negative 1 becomes positive 2. So this is 2 minus y dy. Now can we integrate? All right. V equals pi y from 0 to 1. So what do we get? Pi times 1. Plus pi. Can't do that on this one. I'm going to have to actually do some stuff.
2y minus y squared over 2.
Okay. Well, that's pi. Plus pi times. So 4 minus 2, then minus 2 minus 1/2. Okay. So we got 4 minus 2. We got 2 minus 1/2. 3 halves. So we got 2 minus 3 halves. 1/2. So this is V equals pi plus pi over 2, which is 3 pi over 2. There's your answer. One more washer method example here. A manufacturer drills a hole through the center of a metal sphere of radius 5 inches. The hole has a radius of 3 inches. What is the volume of the resulting metal ring? So what we had was a solid metal ball. And then somebody took and put this in a vise or something, and then they bored a hole straight through it. So we're left with just this shell. That's the resulting metal ring. we want to figure out how much material is in that resulting ring. So find the volume. The sketch for that in a cross-section format is given by this. So what do we do? Like, do you see how this forms this?
Yeah.
Okay. So if this forms this, then what are we revolving about? Good. It can't be the y-axis because that's just going to give me this flat shape here. Not good. It has to be the x-axis. Now what? So what do we do? Figure out what your equations are. What are the equations?
So we're going to have yeah.
Y equals 3 for that.
Someone get that one. I got Y equals 3.
Yeah, that was the tough one for sure.
Something plus 5.
Okay, so in the problem, it says it's a metal sphere, which means that this is a half a circle in a flat plane, right? The equation for a circle is what? No. X squared plus y squared equals r squared. Good. That is the equation for a circle that hasn't been translated off of the origin. Okay, so let's set up a representative rectangle here so that we understand how this thing has to work. I'll put it right here. This slider has to slide all the way from here, whatever that is, to here, whatever that is. Okay? And it does work. We're not going to have any issues with having to split up integrals or anything like that. So this thing slides smoothly. Because of the fact that it's shaped like this, that gives me a delta what? X, which means I need my function solved for y. It needs to be in terms of x. So I'm going to have an outer radius, and I'm going to have an inner radius. Inner radius is easy. It's the outer radius that's going to be tricky. What is r? By r, I mean the radius of our circle here. It is 5. So this r squared right here is actually 5. So now I have x squared plus y squared equals 25. Solve for y. So we subtract x squared from both sides, and then we take the square root, and we have y equals, technically plus or minus the square root of 25 minus x squared. We're dealing with the positive portion, so I just need to write the positive square root. All right, so are we good to set up the integral now, or do we need more information? We need the intersection points. We can see on the graph what they look like, but we need to be sure. So set this equation equal to 3. Square both sides. Add x squared to both sides. Subtract 9 from both sides. Plus or minus 4. So that's our 2 intersection points. Like we thought, but we have to prove it mathematically. So now do we have enough information? All right, so then V equals?
Minus
Integral.
So this is just big R squared minus little r squared. So what should we do next? So what we have sitting here is 25 minus x squared minus 9. So combine like terms and we have 16 minus x squared. Okay? All right, v equals pi times. From -4 to 4. Okay, v equals pi times.
-4 times
64.
minus 16 over 3.
4 cubed
No,
is 64 over 3. Minus some stuff.
-64
Plus 64 thirds. There is a minus sign sitting here. What can I do? V equals pi times, I got 64 plus 64, 128, minus 128 thirds.
Now we can common denominator.
We need a common denominator.
Good job.
So what's 128 times 3?
When we had a calculator.
Don't use a calculator. 384? You sure? 384.
We're locking in that.
All right, final answer. 384. 384 thirds minus 128 thirds is something thirds.
Well, this 28 times
256. 256. I can't even write 256 thirds times pi. So 256 pi over 3. There's your answer. Let's throw on inches cubed for our own enjoyment.